Hello, everybody. Welcome to this video on learning mathematics through concepts and examples. In this video, I'm going to show you how you can use the algebraic methods to find limits. Let's get started. So here I have two examples on this slide. Let's solve A first and we go to B. So in A, we have to find the limit as x approaches to 3 of a linear function. So we have a limit as x approaches to 3 of a linear function 3x plus 1. So please note, whenever you are calculating the limit of polynomial function, you can find the limit using direct substitution. So that means this is a linear function, a polynomial function, so we can perform the direct substitution. So this limit will be equal to 3 times the value of x is 3 plus 1, which is equal to 10. Okay, now let's look at B. In B, we have to find the limit as x approaches to, let me write, limit as x approaches to -1 of 2x squared minus 2 over x plus 1. We try direct substitution. That's our first step. So if you try direct substitution there, you'll see that your denominator will be 0. Because if you plug in -1, -1 plus 1, that will be 0. So we cannot find that limit by direct substitution. So the other technique that we can do is for this type of function that involve a polynomial in numerator and denominator, we can factor and cancel. So if we try to factor this, okay, we have limit as x approaches to -1. In the numerator, we can factor out 2. So we get x squared minus 1 over x plus 1. So clearly, we cannot cancel these two yet. But the quantity inside the parenthesis in numerator is x squared minus 1, which can be factored using the difference of squares. So we can rewrite that as, let me write here, that is limit as x approaches to -1, 2 times x plus 1 times x minus 1 over x plus 1. So by doing that, we have x plus 1 in the denominator, x plus 1 in the numerator. We can cancel that. And we are left with limit as x approaches to -1, 2 times x minus 1, which is same as 2 times x, 2x, and then minus 2 times 1, that's a 2. So just like in the first part here, we get a linear function. So when you have a linear, we can just substitute and find the value of the limit. So that will be equal to 2 times -1 minus 2, which will be equal to 2 times -1 is -2 minus 2, that's a -4. So that is equal to -4. So we can factor and cancel the term that makes the denominator 0, and we can do the direct substitution and get the limit. Okay, that is our first example. Let's move to the second example here. So here also I have two examples. Let's solve A first, and we'll go to B. So in A, we have to evaluate the limit as x approaches to 4, square root of x minus 2 over x minus 4. Let me write it down. So we have limit as x approaches to 4 of square root of x minus 2 over x minus 4. If we try direct substitution, again, 4 minus 4, the denominator will be 0. So we cannot perform the direct substitution. But what we have to do here is, because it has a root in the numerator, we have to multiply both numerator and denominator by the conjugate of the numerator. So we multiply here by square root of x plus 2 over square root of x plus 2. Because by doing this, we'll be able to cancel this x minus 4, which makes the denominator 0. Now, what we get is limit as x approaches to 4. In the numerator, square root of x minus 2 times the square root of x plus 2. This is like a minus b times a plus b, which is a squared, or square root of x squared is x, minus b squared, 2 squared is 4. And in the denominator, I'm multiplying these two. So x minus 4 times square root of x plus 2. So you can clearly see that we have x minus 4 in the numerator, x minus 4 in the denominator. We can cancel that. And we get limit as x approaches to 4 of 1 over square root of x plus 2. So now we can perform the direct substitution, because if we substitute 4 in the denominator, numerator remains the same. In the denominator, this will be square root of 4, which is 2 plus 2, that is a 4. So our limit is 1/4 there. Okay, now let's go here. In this one, we have to find the limit as x approaches to 3 from the left. So if we try direct substitution here, you can see that 3 minus 3 will be 0, denominator will be 0, but there is nothing we can factor and cancel. So in this one, we have to think critically here. See, when x approaches to 3 from the left, okay, from the left, the numerator does not change, it remains 2. But the denominator, see, x approaches to 3 means this x is very, very close to 3. That means when this number is very close to 3 and that is a 3, the difference is a very, very small number. Okay, and the other thing is, because x approaches to 3 from the left, x is smaller than 3. A smaller number minus a bigger number is a negative. So we get a very small negative number. Negative, so we can write very, very small, okay, very small negative. Let me write minus NV for negative number. So we end up getting, you have a positive in the numerator, positive divided by negative is a negative. So our result here is negative. And a finite number, 2 is a finite number, divided by very, very small number. When you divide a finite number by very, very small number, it will be really, really large, which can be represented by infinity. Okay, that is our second example. Let's move on to next example now. Okay. So here is our next example. Here also we have two problems. So let me solve A first, and then we go to B. So in A, we have limit as x approaches to 0 from the right of 5 plus x over x. I just want to rewrite this little bit. Limit as x approaches to 0 from the right of, see, we have 5 divided by x. I can write that as 5 over x, and then plus x over x, that is a 1. So that's what we get. Now, when x approaches to 0, when we say x approaches to 0 from the right, that means this number is really, really close to, okay, close to 0. Very, very small number, close to 0. It's a positive number because it is approaching from the right. Okay, approaching from the right towards 0 means it's a positive number, but it's a very, very small number. So when you divide a 5 by a very, very small number, okay, when you divide 5 by a very, very small number, that's going to be a very, very large quantity. So we write infinity. And then the limit of the constant, limit of 1, is just 1. So a very, very large number represented by infinity here in this case, okay, plus 1. So infinity plus 1, that is infinity. So this limit happens to be infinity. Okay, let's go to the second example on this slide. We have to find the limit as x approaches to infinity. Let me write it. So we are looking for limit as x approaches to infinity of 1 plus 8 over x cubed. And you can clearly see that this one looks quite similar to this one here. But let's see what we get. First of all, the limit of the constant. Okay, limit of 1, when x approaches to infinity or x approaches to any value, the limit of constant is just that constant, so which is 1. Which is 1. Then plus 8 over x cubed. X approaches to infinity, meaning of that is x is really, really large. And if you cube that, it is in fact very, very large. So when you divide 8 by very, very large, or when you divide 8 into very large number of parts, the result will be approximately 0. So that is 0. So 8 divided by really large quantity, that would be 0. So we get 1 plus 0, which is equal to 1. So that's how we can find that limit. Okay, let's do one more example, one more slide. Here also we have two examples. So we are going to do A first and then B. Let's look at A. See, in A, we have to find the limit of a polynomial function as x approaches to infinity. So x approaches to negative infinity. When you're calculating the limit as x approaches to positive or negative infinity, we are actually looking at the end behavior. And what we know is for the polynomial function, the end behavior is, okay, end behavior is given by the leading term only. So what I mean by that is limit as x approaches to negative infinity of 3x cubed plus 1000x squared plus 2 is same as the limit as x approaches to negative infinity of 3x cubed, because the end behavior of the polynomial function is just determined by the leading term. That's why we can just write that. And you can see when x approaches to infinity, in this case negative infinity cubed. Negative cubed is negative, so our result will be negative, and then infinity cubed times 3, that's infinity. That is infinity. So we get that limit as negative infinity. So meaning of that is on the left end, the graph of this function will go towards negative infinity. That is the meaning of that. Okay, here's the next one, B. We have to find the limit as x approaches to infinity of this rational function. So you can see that the highest power in the denominator of this one is x cubed. So in order to find this one, we divide by the highest power. So what I mean by that is we do this. Limit as x approaches to infinity. We have 2x cubed. We divide by x cubed. The x with the highest power in the denominator is x cubed. So we divide everything by x cubed. Then plus 59x squared over x cubed. Same thing here, x cubed over x cubed. And then minus 1000 over x cubed. Okay. Now let's cancel those x and see what we get. Limit as x approaches to infinity. So x cubed canceled. So that will be 2 plus 59 over x squared cancel. So we are left with x. So 59 over x. X cubed over x cubed, that's a 1. Then minus 1000 over x cubed, which is equal to, since x approaches to infinity, x is very, very large. So this will be 2 plus 59 divided by very large quantity is 0. And then over 1 minus 1000 divided by really, really large quantity. That is also approximately 0, which is equal to 2. So that means the limit of this rational function is 2. Also remember, because we are calculating the limit as x approaches to infinity, this is the end behavior. That means if you go towards the right end, the graph of this function approaches closer and closer to a horizontal line, y equal to 2. Or y equal to 2 is the horizontal asymptote to the graph of this function. Okay, that's all in this video. I hope you find this video helpful. Thank you so much for watching.